Have you ever pondered profound questions about our existence and the origins of the universe itself? To unlock the mysteries of our existence, we must embark on a journey to the very first moments of the cosmos. Exploring the inception of the universe is the key to understanding our place within it. What was the birth of the universe like? And what forces set everything into motion? Equally intriguing is the contemplation of the universe's ultimate destiny. Will it endure for all eternity, continually expanding and evolving? Or is there a day when it might meet its demise? In our quest to unravel this profound subject, we turn to a multitude of well-established scientific theories and experiments. This journey takes us on a voyage, traveling back to the very origins of cosmology and extending into the distant future of our cosmos. Within this exploration, we'll dive into the leading theories, empirical evidence, and the remarkable narrative of the universe's birth and its ultimate fate. This will be a video series. In this first episode, we will delve into the subject of how our knowledge of the universe has evolved over time. So, let's commence our video journey. From the earliest days of human civilization, our ancestors looked up at the night sky with wonder and curiosity, trying to make sense of the celestial mysteries overhead. Over the centuries, this quest for knowledge has led to a remarkable journey of scientific discovery, challenging long-held beliefs and reshaping our perception of the cosmos. The earliest recorded observations of the cosmos date back to ancient civilizations such as the Babylonians, Egyptians, and Greeks. The Babylonians were the first to develop a system of astrology, which was later adopted by the Greeks and Romans. In this exploration of the evolution of our understanding of the universe, we embark on a voyage through time, from the geocentric notions of ancient civilizations to the groundbreaking revelations of modern astrophysics. Along the way, we'll uncover the revolutionary theories and experiments that have propelled us toward a deeper comprehension of the cosmos, forever altering our perspective on the universe and our place within it. Cosmology is indeed a fascinating field that seeks to understand the universe as a whole rather than focusing on individual celestial objects. In a nutshell, it asks profound questions about the cosmos and its evolution. It delves into the origins of the universe, the existence of stars, galaxies, and galaxy clusters, and the future of the cosmos. Cosmology aims to create a comprehensive and large-scale picture of the nature of the universe, offering insights into the fundamental workings of the cosmos. It's a science that explores the grand tapestry of the universe, seeking to unravel its mysteries and understand our place within it. A well-known scientist, some say it was Bertrand Russell, once gave a public lecture on astronomy. In his lecture, he explains the established scientific understanding that the Earth orbits around the Sun, and the Sun, in turn, orbits around the center of our galaxy. After the scientist's explanation, a little old lady at the back of the room stands up and challenges his explanation. She posits a different view, asserting that the world is a flat plate supported on the back of a giant tortoise. This is a humorous and fantastical alternative to scientific understanding. The scientist responds with a somewhat condescending smile and poses a question. What is the tortoise standing on? He is essentially asking for an explanation for the tortoise's existence and support. The old lady, undeterred, replies with the memorable phrase, "But it's turtles all the way down." She suggests that the tortoise, in her belief, is standing on another turtle, and this sequence of turtles supporting each other continues infinitely. The anecdote is a humorous illustration of a classic philosophical problem known as the infinite regress or turtles all the way down. The idea of the universe as an infinite tower of tortoises was a speculative concept that was used to describe the cosmological model in the past. Our current understanding of the universe is based on scientific observations, experiments, and theoretical models. These models have been developed and refined over centuries, incorporating a vast body of evidence from various fields of science such as astronomy, physics, and cosmology. Our knowledge of the universe is based on scientific theories and observations. We know that the universe is vast, expanding, and composed of galaxies, stars, planets, and various forms of matter and energy. We have learned this through the use of telescopes, space probes, particle accelerators, and mathematical models. For example, the discovery of cosmic microwave background radiation provided strong evidence for the Big Bang theory, which explains the origin and expansion of the universe. The origin of the universe is explained by the Big Bang theory, which suggests that the universe began as a singularity and has been expanding ever since. The future of the universe is a topic of ongoing research, but there are different scenarios such as the Big Freeze, Big Crunch, or Big RIP, depending on the rate of expansion and the influence of dark energy. The Big Bang theory suggests that the universe had a beginning about 13.8 billion years ago. In 2021, a new study claimed that the age of the universe is 26.7 billion years. However, this claim is not widely accepted by the scientific community and has been met with skepticism. What happened before the Big Bang, if anything, is still a topic of debate and speculation. Some theories propose that the concept of before may not apply to the universe's origin, as time itself may have originated with the Big Bang. The nature of time is a complex topic in physics and philosophy. Time is a fundamental aspect of our universe, and it is related to the fabric of spacetime. It can be influenced by factors like gravity. Whether time will come to an end or if time travel is possible remains a subject of research and speculation, often explored in the context of theories like general relativity and quantum mechanics. Why do we dismiss the idea of the universe as an infinite tower of tortoises? And what do we truly understand about the cosmos, and how did we come to these understandings? Where did the universe originate, and what is its ultimate fate? Was there a definite beginning, and if so, what occurred before it? Time's nature, its potential end, and the possibility of traveling back in time are intriguing questions. Recent advancements in physics, aided by remarkable technologies, offer potential answers to some of these age-old queries. These answers may, in the future, appear as self-evident as the Earth orbiting the Sun, or they could be as far-fetched as a stack of tortoises. Only time, whatever that concept entails, will reveal the truth. As far back as 340 BC, the Greek philosopher Aristotle made compelling arguments for the Earth's spherical shape. He recognized that lunar eclipses were caused by the Earth positioning itself between the Sun and the Moon. The Earth's shadow on the Moon consistently appeared round, which would only happen if our planet was spherical. If the Earth had been a flat disk, the shadow would have been elongated and elliptical, unless the eclipse always occurred at a time when the Sun was directly under the center of the disk. Additionally, the Greeks observed that the North Star appeared lower in the sky when viewed from the south, compared to more northern regions. Aristotle even used this to estimate the Earth's circumference, noting that the difference in the North Star's apparent position in Egypt and Greece indicated a distance of approximately 400,000 stadia around the Earth. While the exact length of a stadium is uncertain, it might have been about 200 yards, making Aristotle's estimate roughly twice the currently accepted measurement. The Greeks also had a third argument supporting the Earth's roundness, the phenomenon of seeing a ship's sails appear on the horizon before the hull became visible. Aristotle's cosmological model indeed posited that the Earth was stationary and that the celestial bodies, including the Sun, Moon, planets, and stars, moved in circular orbits around the Earth. This geocentric view was influenced by Aristotle's belief in the Earth as the center of the universe for mystical reasons, and he associated circular motion with perfection. This geocentric model was further developed by Claudius Ptolemy in the 2nd century AD. In Ptolemy's model, the Earth was positioned at the center of the universe, surrounded by a series of nested spheres. These spheres carried celestial objects, including the Moon, Sun, stars, and the 5 known planets of the time: Mercury, Venus, Mars, Jupiter, and Saturn. Ptolemy's system, known as the Ptolemaic model, was widely accepted for many centuries and was used to predict the movements of celestial bodies, even though it had certain inaccuracies. It wasn't until later developments in astronomy, particularly the heliocentric model proposed by Copernicus, that a more accurate understanding of the solar system's structure emerged. In the Ptolemaic model, to account for the complex observed movements of the planets in the sky, it was proposed that the planets themselves moved on smaller circles that were attached to their respective spheres. These smaller circles, known as epicycles, were a way to explain the planet's apparent retrograde motion and other deviations from simple circular orbits. The outermost sphere in this model was dedicated to the fixed stars. These were the stars that appeared to maintain their positions relative to each other and seemed to rotate together across the night sky. In this geocentric view, these fixed stars were considered to be on the outermost celestial sphere. It's important to note that, in this geocentric cosmological framework, what lay beyond the last celestial sphere was not made very clear. It was generally understood that this region was beyond the scope of humanity's observable universe, and there was limited conceptualization of what might exist beyond the outermost sphere. This model was developed at a time when our understanding of the cosmos was quite limited compared to modern astronomy. Ptolemy's model was indeed quite accurate in predicting the positions of celestial bodies in the sky, considering the knowledge and observations available at the time. However, it had a specific assumption about the moon's motion that led to a peculiar consequence. Ptolemy assumed that the moon followed a path that brought it sometimes twice as close to the Earth as at other times. This assumption implied that the moon should appear to change in size, sometimes appearing twice as large as at other times. Ptolemy was aware of this apparent flaw in his model, but despite it, his geocentric model was widely accepted, although not universally. One of the reasons for its widespread acceptance was its compatibility with the prevailing religious beliefs of the time. The Christian Church, for example, embraced Ptolemy's model as it seemed to align with the interpretation of Scripture. Additionally, this model had the advantage of leaving ample space beyond the sphere of fixed stars for heaven and hell, which was in accordance with the theological teachings of the time. It wasn't until the Renaissance and the work of astronomers like Nicolaus Copernicus and Johannes Kepler that a heliocentric model gained traction, eventually leading to a more accurate understanding of the solar system and a departure from the geocentric view. In 1514, a simpler and more revolutionary model was proposed by the Polish priest Nicolaus Copernicus. Initially, possibly due to the fear of being labeled a heretic by the Church, Copernicus circulated his model anonymously. His groundbreaking idea was that the Sun was stationary at the center of the solar system, and the Earth, along with the other planets, orbited the Sun in circular orbits. However, it took nearly a century for this concept to gain significant acceptance. It wasn't until the work of two astronomers, the German Johannes Kepler and the Italian Galileo Galilei, who publicly supported the Copernican theory, that it began to be taken more seriously. Although the orbits predicted by the Copernican model did not perfectly match the observed planetary paths, this marked a significant shift in scientific thought. The final blow to the Aristotelian/Ptolemaic geocentric theory came in 1609, when Galileo Galilei began observing the night sky with a newly invented telescope. When he turned his telescope toward the planet Jupiter, he made a remarkable discovery. Galileo observed that Jupiter had several small satellites or moons orbiting around it. This observation indicated that not everything had to revolve directly around the Earth, as Aristotle and Ptolemy had proposed. While it was still possible to argue that the Earth was stationary at the center of the universe, and that Jupiter's moons followed incredibly complex paths around the Earth, Copernicus's heliocentric theory offered a much simpler explanation. Around the same time, Johannes Kepler modified Copernicus's model by suggesting that the planets did not move in perfect circles, but in ellipses, which are elongated circles. This adjustment to the Copernican model finally aligned its predictions with the observed movements of celestial bodies, marking a significant step in the transition from the geocentric to the heliocentric model of the solar system. Johannes Kepler initially considered elliptical orbits as an ad hoc hypothesis and found them somewhat unappealing because, in his view, ellipses were less perfect than circles. He stumbled upon the idea that elliptical orbits fit the observations well, but had difficulty reconciling this with his belief that planets were compelled to orbit the Sun due to magnetic forces. A full explanation for planetary motion came later, in 1687, with the publication of Sir Isaac Newton's Philosophiae Naturalis Principia Mathematica, a work often considered one of the most significant in the history of the physical sciences. Newton not only presented a comprehensive theory of how bodies move in space and time, but also developed the complex mathematics required to analyze these motions. Furthermore, Newton introduced the concept of universal gravitation, which stated that every body in the universe was attracted to every other body by a force that became stronger as the masses of the bodies increased and as they came closer to each other. This same force was responsible for objects falling to the ground. It's worth noting that the popular story of an apple falling on Newton's head is likely apocryphal. What he actually said was that the idea of gravity came to him during a contemplative moment and was prompted by the fall of an apple. Newton's theory showed that gravity was responsible for the Moon's elliptical orbit around the Earth, and for the planets, including Earth, following elliptical paths around the Sun. This revolutionary understanding effectively replaced the older geocentric models, including Ptolemy's celestial spheres, and the concept of a natural boundary to the universe. With fixed stars appearing to maintain their positions, except for a rotation across the sky due to Earth's own rotation, it became natural to assume that these fixed stars were objects like our Sun, but situated at much greater distances in the cosmos. Sir Isaac Newton recognized a challenging aspect of his theory of gravity in relation to the stars. According to his theory, stars should exert gravitational attraction on each other, which raised the question of whether they could remain essentially motionless, or if they would eventually fall together. In a letter written in 1691 to another prominent thinker of his time, Richard Bentley, Newton argued that if there were a finite number of stars distributed over a finite region of space, they would indeed fall together at some point due to their mutual gravitational attraction. However, Newton reasoned that if there were an infinite number of stars distributed more or less uniformly over infinite space, they would not collapse in on themselves because there wouldn't be a central point for them to converge toward. This argument touches on some of the complexities and paradoxes associated with infinity. In an infinite universe, every point could be considered the center because, from any point, there are an infinite number of stars in all directions. However, this notion of an infinite, static model of the universe, where gravity is always attractive, faced challenges. It was only much later that the correct approach was realized. When considering a finite situation in which stars gravitate toward each other, it became apparent that if more stars were added uniformly outside this region, Newton's law of gravity indicated that the extra stars would have no impact on the original ones on average. Consequently, they would still collapse in on themselves. This realization led to the understanding that it's impossible to maintain an infinite, static model of the universe in which gravity is always attractive. The notion that the universe could be expanding or contracting, as we now understand it through the Big Bang theory, was not a common idea before the 20th century. Prior to that time, there were generally two prevailing views. 1. The steady-state universe. It was widely accepted that the universe had existed forever in an unchanging state. This idea was based on the belief in eternal truths, and people found comfort in the notion that the universe itself was eternal and perpetually constant. 2. Creation at a finite time. An alternative perspective was that the universe had been created at some finite time in the past, more or less in the form that we observe it today. This view was often in line with religious or mythological accounts of creation, and had its own cultural and philosophical significance. The concept of an expanding universe and the idea that it had a finite beginning came to the forefront in the early 20th century with the development of the Big Bang theory. This theory, supported by observations like the redshift of distant galaxies, provided a compelling scientific explanation for the origin and evolution of the universe. It was a significant departure from the earlier ideas of a steady state or eternal universe, and it has since become the prevailing cosmological model. This shift in understanding marked a fundamental transformation in our perception of the universe and its history. Prior to the understanding of an expanding universe and the Big Bang theory, those who recognized that Newton's theory of gravity suggested a static universe attempted to modify the theory to maintain a state of equilibrium. They introduced the idea that gravitational forces could become repulsive at very large distances. This modification allowed for an infinite distribution of stars to remain in equilibrium, with attractive forces between nearby stars balanced by the repulsive forces from those farther away. The goal was to avoid gravitational collapse in an infinite universe. However, this idea of a repulsive force at great distances was based on the assumption that such an equilibrium would be stable. In reality, a slight change in the distances between stars in some regions would disrupt this balance. If stars moved even slightly closer, the attractive forces would strengthen, leading to a collapse. Conversely, if stars moved slightly farther apart, the repulsive forces would dominate and drive them even farther apart, making the equilibrium unstable. Another objection to the concept of an infinite static universe was raised by the German philosopher Heinrich Olbers in 1823. He highlighted the paradox that in an infinitely static universe, with nearly every line of sight ending on the surface of a star, the entire night sky should be as bright as the sun, even during the night. Olbers' counter-argument was that light from distant stars would be absorbed by intervening matter. However, this led to the paradox that the intervening matter should heat up and emit light as brightly as the stars. The only way to resolve this paradox was to consider that the stars had not been shining eternally, but had turned on at some finite point in the past. In such a scenario, the absorbing matter might not have heated up yet, or the light from distant stars might not have reached us, explaining the darkness of the night sky. This then raised the question of what could have triggered the stars to turn on in the first place, a question that laid the foundation for future developments in cosmology. The question of the beginning of the universe has a long history of discussion in various cosmologies and religious traditions, including the Jewish, Christian, and Muslim faiths. In many of these traditions, it was believed that the universe had a finite and relatively recent starting point. One argument for such a beginning was the concept of a first cause. This idea posited that it was necessary to have a fundamental cause to explain the existence of the universe itself. While events within the universe could be explained as one event leading to another, the existence of the universe as a whole required an ultimate origin. St. Augustine, in his book The City of God, presented another argument for a finite beginning of the universe. He pointed out that human civilization was making progress, and people remembered who had achieved particular deeds or developed specific techniques. Therefore, it seemed unlikely that humanity, and by extension, the universe, had been around for an excessively long time. St. Augustine even suggested a date of approximately 5000 BC for the creation of the universe, based on the Book of Genesis. This date was not significantly distant from the end of the last ice age, around 1000 BC, a period marked by the emergence of early civilizations, according to archaeological findings. These discussions reflected ancient attempts to grapple with the concept of the universe's origin and its place in human history and understanding. Aristotle and many other Greek philosophers held the view that the idea of a creation event was unappealing because it seemed to imply divine intervention. They believed that both the human race and the world had existed eternally and would continue to do so forever. In response to the argument about progress, the ancients proposed that periodic floods or other disasters had repeatedly set human civilization back to its beginnings, thus accounting for apparent cycles of progress and decline. The questions of whether the universe had a beginning in time and whether it had spatial limits were later explored in depth by the philosopher Immanuel Kant in his work Critique of Pure Reason, published in 1781. Kant referred to these questions as antinomies or contradictions of pure reason because he saw equally compelling arguments for both sides. Kant's argument for the thesis that the universe had a beginning was based on the notion that without a beginning, there would be an infinite period of time before any event, which he found absurd. His argument for the antithesis, that the universe had existed forever, was rooted in the idea that if the universe had a beginning, there would be an infinite period of time before it. Essentially, both cases were based on the unspoken assumption that time extended infinitely into the past, regardless of whether the universe itself was eternal. However, this concept of time continuing forever into the past was later challenged. It was St. Augustine who pointed out that the concept of time lacked meaning before the beginning of the universe. When asked what God did before creating the universe, Augustine didn't respond with humor but suggested that time was a property of the universe itself, created by God, and that it didn't exist before the universe's inception. This idea fundamentally changed the way philosophers and scientists thought about the nature of time and the universe's origins. Before the groundbreaking observations made by Edwin Hubble in 1929, the question of whether the universe had a beginning was largely a matter of metaphysics or theology. The idea of a static and unchanging universe was widely accepted, and it was possible to explain the observed phenomena equally well with the universe having existed forever or with it having been set in motion at a finite time in a way that made it appear eternal. However, Hubble's discovery was a turning point in our understanding of the universe. His observations showed that distant galaxies were rapidly moving away from us, indicating that the universe was expanding. This implied that at earlier times, galaxies and objects in the universe would have been much closer together. In fact, it suggested that there was a time, roughly 10 to 20 billion years ago, when all matter in the universe was concentrated at the same point, leading to an infinite density. Hubble's discovery fundamentally transformed the question of the universe's beginning. It shifted the topic from the realm of metaphysics and theology into the domain of science. The concept of an expanding universe laid the foundation for what later became the Big Bang theory, which describes the universe's evolution from an extremely dense and hot state to its current form. This shift marked a significant milestone in our understanding of the cosmos. Hubble's observations suggested the existence of a moment known as the Big Bang when the universe was incredibly small and infinitely dense. In such extreme conditions, the usual laws of science would break down, making it impossible to predict what occurred before this time. Events that transpired earlier than the Big Bang would have no observable consequences and could essentially be ignored. This concept implies that time had a beginning at the Big Bang, meaning that earlier times would have no meaningful definition. It's crucial to understand that this idea of a beginning in time is fundamentally different from earlier notions. In a static and unchanging universe, any beginning in time would have to be imposed by some external force or being, as there's no inherent physical necessity for such a beginning. In this view, one could imagine a scenario where God created the universe at any moment in the past. However, in an expanding universe, there are physical reasons that suggest the necessity of a beginning. While it's still conceivable that God created the universe at the instant of the Big Bang, or even afterward, in a way that mimics a Big Bang, it would be meaningless to suggest that the universe was created before the Big Bang. An expanding universe doesn't necessarily rule out the existence of a creator, but it does place constraints on when such a creative act might have occurred. To discuss the nature of the universe and address questions about its origins and ultimate fate, it's essential to have a clear understanding of what a scientific theory is. In the upcoming episodes, we will delve deeply into the origins and ultimate destiny of the universe. In its simplest form, a theory can be considered a model of the universe or a specific part of it. It consists of a set of rules that connect elements within the model to the observations we make. Importantly, a scientific theory exists solely in our minds and doesn't possess any other form of reality. The quality of a scientific theory is evaluated based on two key criteria. First, it must accurately describe a wide range of observations using a model that contains only a few arbitrary elements. Second, it should provide precise predictions about the outcomes of future observations. For example, Aristotle held the belief in Empedocles' theory that everything was composed of four elements: earth, air, fire, and water. While this theory was relatively simple, it didn't lead to any specific predictions about observations. On the other hand, Sir Isaac Newton's theory of gravity was based on an even simpler model. It was proposed that bodies attracted each other with a force directly proportional to their mass and inversely proportional to the square of the distance between them. Despite its simplicity, Newton's theory successfully predicted the motions of celestial bodies like the Sun, the Moon, and the planets with a high degree of accuracy. In summary, a good scientific theory should provide a simple model that accurately describes a wide range of observations and offers clear predictions for future observations. This is the foundation of our understanding of the universe and the development of scientific knowledge. Any physical theory is fundamentally provisional, and it exists as a hypothesis. It can never be definitively proven to be true. Regardless of how many times experimental results align with a theory, there is always the possibility that the next experiment may yield results that contradict the theory. However, you can disprove a theory by finding a single observation that contradicts its predictions. The philosopher of science Karl Popper highlighted a key aspect of a good scientific theory. It is characterized by making predictions that, in principle, could be disproven or falsified by observation. When new experiments consistently agree with a theory's predictions, our confidence in the theory grows. Nevertheless, if a new observation contradicts the theory, we must either abandon or modify the theory to account for this inconsistency. This principle underscores the dynamic and self-correcting nature of the scientific method. The constant testing of theories against empirical evidence ensures that scientific knowledge evolves and improves over time. It also means that even long-standing scientific theories are open to revision or replacement in the face of new evidence, which is a fundamental strength of the scientific approach. At least that is what is supposed to happen. But you can always question the competence of the person who carried out the observation. In the practice of science, it is indeed possible to question the competence of the individual who conducted an observation, especially when experimental results seem to contradict an established theory. However, the scientific community employs rigorous peer review processes replication of experiments, and constant scrutiny to minimize such issues. In many cases, when new observations or experiments appear to conflict with an existing theory, the scientific approach is to explore whether a new theory or an extension of the previous theory can account for the observed discrepancies. This process of refining and extending theories based on new data is a fundamental part of scientific progress. For instance, accurate observations of the planet Mercury indicated a small discrepancy between its motion and the predictions of Sir Isaac Newton's theory of gravity. Albert Einstein's general theory of relativity provided a slightly different prediction for Mercury's motion. When Einstein's predictions matched the observed data while Newton's did not, it was a critical confirmation of the new theory. Despite these differences, Newton's theory of gravity is still widely used in many practical situations because the discrepancies between its predictions and those of general relativity are minimal in most everyday scenarios. Additionally, Newton's theory is simpler and more straightforward to work with than Einstein's theory of general relativity. This illustrates the balance in science between adopting the most accurate and comprehensive theories when needed and using simpler, effective models for practical purposes. The ultimate aspiration of science is to provide a single, comprehensive theory that describes the entire universe. Nevertheless, in practice, most scientists adopt a two-part approach to this complex problem. The first part involves formulating the physical laws that describe how the universe changes over time. These laws specify how the universe's state at one time will evolve into its state at a later time. Understanding these laws is a fundamental aspect of scientific inquiry. The second part concerns the question of the initial state of the universe. Some scientists believe that science's primary domain is the first part, namely, the laws that govern how the universe evolves over time. They consider the question of the universe's initial state a matter of metaphysics or religion. From this perspective, they may argue that an omnipotent deity, like God, could have initiated the universe in any manner, and this initiation could be arbitrary. However, this viewpoint is challenged by the fact that the universe appears to develop in a highly regular and law-governed way. The consistent and orderly evolution of the universe suggests that there are laws governing the initial state as well. In other words, it is reasonable to assume that both the laws describing the universe's evolution and the laws governing its initial state exist. This dual approach reflects the current scientific understanding and acknowledges the connection between the laws governing the universe's behavior over time and those that govern its initial conditions. Scientists strive to unravel both aspects to gain a complete understanding of the cosmos. Describing the universe as a whole in a single theory has proven to be an exceptionally challenging endeavor. Instead, the approach taken by scientists is to break down this complex problem into smaller, more manageable parts and develop a series of partial theories. Each of these partial theories is designed to describe and predict a specific set of observations, often by simplifying or neglecting the effects of other factors and representing them with straightforward numerical values. This approach may raise questions about whether it is fundamentally flawed. It is possible that if all aspects of the universe are interconnected in a fundamental way, attempting to solve parts of the problem in isolation may be insufficient to reach a complete understanding. Nevertheless, this method has been the path of progress in scientific inquiry. One of the most prominent examples is Sir Isaac Newton's theory of gravity. It shows that the gravitational force between two objects depends solely on one characteristic of each object, its mass, and is essentially independent of the object's composition. In other words, you don't need to understand the intricate structure and composition of celestial bodies to calculate their orbits. In the present day, scientists employ two fundamental partial theories: the general theory of relativity and quantum mechanics. The general theory of relativity deals with gravity and the large-scale structure of the universe, while quantum mechanics is concerned with phenomena on extremely small scales. Unfortunately, these two theories are known to be inconsistent with each other, which poses a significant challenge. A primary focus of modern physics is the search for a new theory that can successfully merge these two frameworks, a quantum theory of gravity. While such a theory has not been fully developed, we do have some insights into the properties it must possess. As we delve into later episodes, we will explore the requirements and predictions of a quantum theory of gravity, shedding light on the ongoing quest to unify these fundamental theories. Believing that the universe is not arbitrary but instead follows specific laws leads to the necessity of combining the partial theories into a comprehensive, unified theory that can describe all aspects of the universe. This unified theory, often referred to as a theory of everything, aims to provide a single framework to account for all phenomena in the universe. However, there is a fundamental paradox in the pursuit of such a complete, unified theory. The concepts of scientific theories are built on the assumption that we are rational beings who can freely observe the universe, make logical deductions from our observations, and construct theories accordingly. This paradox arises from the fact that a theory of everything, if it exists, would also describe the nature of our rationality and the process of scientific inquiry itself. In other words, the theory would encompass everything, including our capacity to formulate theories and our understanding of the laws governing the universe. This leads to a self-referential aspect of the theory, which can be challenging to reconcile. In essence, the search for a complete, unified theory forces us to confront the question of whether the theory can encompass itself and explain its own existence. This is a deep and complex philosophical issue that adds an extra layer of complexity to the quest for a theory of everything. In a scheme where we seek a complete, unified theory to understand the laws governing the universe, it is reasonable to assume that we can make progress and approach a deeper understanding of the universe. However, the paradox arises when considering that such a theory, if it exists, would also determine not only the fundamental laws of the universe, but also our own actions and reasoning. This leads to a perplexing question. If the complete unified theory governs all aspects of the universe, including our thoughts and actions, would it not also determine the outcome of our quest to discover it? In other words, the theory itself could dictate whether we arrive at the correct conclusions, draw incorrect conclusions, or even prevent us from reaching any conclusion at all. This paradox raises profound philosophical and epistemological questions about the nature of human knowledge, free will, and determinism. It questions whether we have the autonomy to explore and discover the theory, or if the theory itself predetermines our path and outcomes. It's a challenging and thought-provoking issue that has been the subject of much debate and discussion among scientists and philosophers. To address the paradox of whether a complete, unified theory might predetermine our ability to discover it, one possible answer draws inspiration from Darwin's principle of natural selection. The key idea is that in any population of self-reproducing organisms, there are variations in genetic material and upbringing among individuals. These variations mean that some individuals will be better equipped than others to make accurate observations about the world and to make decisions based on those observations. Over time, individuals with superior reasoning abilities will have a survival advantage, leading their behavior and thought patterns to become more prevalent in the population. Historically, intelligence and scientific discovery have conferred a survival advantage. However, in the modern world, with the potential dangers posed by scientific discoveries, this advantage is less clear. Even a complete, unified theory may not significantly impact our chances of survival. Nevertheless, if the universe has evolved in a consistent and orderly manner, it is reasonable to expect that the reasoning abilities natural selection has bestowed upon us will also be applicable in our quest for a complete, unified theory. This suggests that our reasoning would not necessarily lead us to incorrect conclusions. In other words, our capacity for rational thought and scientific inquiry, shaped by natural selection, should be a valid and reliable tool in our pursuit of knowledge, including the search for a comprehensive theory of the universe. It emphasizes that our fundamental reasoning abilities, which have evolved over time, are likely to serve us well in this endeavor. The search for the ultimate theory of the universe may seem difficult to justify on practical grounds because the partial theories we already possess are sufficient to make accurate predictions in most everyday situations. However, history has shown that similar arguments could have been made against theories like relativity and quantum mechanics. And yet these theories have led to significant advancements such as nuclear energy and the microelectronics revolution. While it's true that the discovery of a complete, unified theory might not directly impact our species' survival or drastically alter our day-to-day lives, the quest for such a theory has profound human motivation. Throughout the history of civilization, people have not been content to view events as isolated and inexplicable. Instead, they have yearned to understand the underlying order of the world, and to seek meaning and connection in the vast universe. Today, our desire to know why we are here, where we came from, and to understand the deepest workings of the universe remains a powerful driving force. Humanity's thirst for knowledge, understanding, and exploration is a justification in itself for the ongoing quest for a complete description of the universe in which we exist. Our goal is nothing less than unraveling the mysteries of the cosmos and gaining a comprehensive understanding of the cosmos we call home.